57,885,161. To a computer, that's not a huge number. That's a quite normal size number.
Yeah.
Why does it take so long for the computers to eliminate these as possibilities? Like, surely it doesn't take long to get to 2 to that and then check the divisors. And you've only got to find one divisor to knock it off its perch. No, you're not a prime number. What's taking all the time here? Why is it so hard?
Well, firstly, in the ones that work, it takes a long time to find, you never find a divisor. That's the whole point, right? So, that game goes on for a long time. The second point is that, the computers, they work on some sort of, base, okay, for example, maybe base 10 or base 2 or whatever. And so one has to, it's kind of subtle in terms of, you can't just deal with fractions. Cancellations aren't so obvious because everything's written in terms of maybe something like, if you do a division, it involves a recurring series, for example. And you can write that as a rational number and things like that. But because it always has to truncate at some point, it makes those calculations difficult. So it's not trivial just to say, and you've got to rule out the possibilities that it's not just an artifact of it, a numerical artifact. Oh, it looks pretty close to a whole number, but is it a whole number? So I take this number and I divide it by whatever, some other huge number, okay? I get another number. It looks quite close to a whole number. Is it a whole number exactly to how many decimal places? It's not obvious, and these are the kind of, you need that level of precision and exactness, and that involves a lot of computational power.
One last thing, whenever we hear about a new Mersenne prime, people start talking about, oh, well, it's good for cryptography. Do you understand what they're talking about?
I actually don't think that these are particularly useful for cryptography per se. I think large prime numbers are useful, but actually just finding yet another one is not particularly useful. I think the biggest uses coming from these are the spin-offs from the technology that's used to literally play the game, I think. So there's also something interesting else I noticed about this number. And a way to sort of picture it, actually, is a nice way to picture how big the number is. So imagine you tried to work out how many ancestors you had, Brady. So let's suppose you did that. Okay, so you start off with you. Okay, so we'll include you in the family tree. So this is Brady here. Okay. Then I go back one generation, and I've got Brady's mum. Okay. Brady's mum, and Brady's dad, okay? So I've now got a total of 3 people in this family tree, okay? And I can keep on going back. Do it again, and I do it again. So I've got 1 person here, 2 here, 4 here, and I keep adding these up, okay? And I keep going back. At which point would I reach a total number of people? Assuming there's no inbreeding going on at any point, and I'm sure that hasn't gone on in your family, Brady, so you're not royal or anything. So assuming there's been no inbreeding going on, how many generations would you have to go back to get this number of people? All right, how many generations would I include? And of course, the answer is 57,885,161.
Is it?
Yeah. To get that number out. Why is it? Well, we can see it here, okay? So these numbers, this 2 to the p minus 1 is really 1 plus 2 plus 2 squared plus blah, 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 all the way up to 2 to the p minus 1, right? 1 plus 2.
Hang on, sorry.
So here you've got 1 plus 2 plus 2 squared plus 2 cubed, you would go on, which is 8, of course, plus 2 to the 4, all the way up to 2 to the p minus 1. And that would count in total p generations, including yourself. Okay? So it's quite amusing to think what would actually you have been like this many generations ago. So, I mean, roughly speaking, I'm not an evolutionary biologist, but I believe about, sort of order, Homo sapiens have been around for about, of order 10,000 generations, maybe a little bit less. We split from our primate cousins around 100,000 or so generations. So this is a lot more. This is 57 million generations. And apparently, I read that it takes, basically, if you want to go from a mouse to an elephant, if you want to evolve from a mouse to an elephant, you take, of order, 25 million generations. So we're talking, basically, that kind of evolutionary scale. So what your ancestors were at the start of all this, I mean, they were probably some sort of little rodent running around somewhere, running away from the dinosaurs or something. So, I mean, it gets quite difficult to actually gauge, you know, what's happening back then because generation times change, and you know. But anyway, I think this super granddad who's right at the top of this tree is probably a mouse.
All comments about evolution and religion, don't leave them under the video. Just send them directly to Tony.